strange, isn't it? Just when you thought you had a handle on reality, the universe throws a curveball. For centuries, brilliant minds grappled with bizarre facts. The idea that light could bend, that space itself could stretch, or that a single particle could somehow be in two places at once. These weren't just curious anecdotes. They were fundamental truths about our cosmos, truths that often seemed to defy common sense, yet were proven again and again by meticulous observation and daring experiments. And among these head-scratchers, perhaps none is more profound, more unsettling, than the idea that time, that relentless ticking force we all feel, might not be what we think it is. You probably won't survive this journey with your old understanding of reality intact, and that's precisely the point. We're about to dive into something far more intricate, far more mind-bending than mere seconds and minutes. Time, in its deepest cosmic sense, is a mystery wrapped in an enigma, and tonight, you and I are going to peel back those layers. Before you and I get into more detail, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Do let me know your local time. Now, settle in. Picture yourself nestled comfortably, perhaps with a blanket pulled up to your chin. You feel the steady beat of your own heart, the rhythmic rise and fall of your breath. These are internal clocks, isn't it? Markers of your own existence.
But what about the universe? Does the cosmos, in its vast indifferent sprawl, have a heartbeat of its own? Does it know what time it is? We perceive time as this constant flowing river, carrying us inevitably from past to future. Every sunrise, every sunset, every birthday, they all mark its passage. We build our lives around it, scheduling appointments, catching trains, living by the clock.
And for good reason, right? Because time marches on, always forward, never backward, or does it? This seemingly simple question, does the universe know what time it is, unlocks some of the most profound, unsettling, and frankly mind-boggling concepts in modern physics. What we casually refer to as time might be nothing more than a convenient human construct, a shared illusion that helps us navigate our day-to-day lives. Think about it. When you look at a clock, you're not seeing time itself, are you? You're seeing the position of hands or digits changing. When you feel a moment pass, you're experiencing a sequence of events.
But is there some underlying universal tick-tock that the entire cosmos adheres to? Is there a cosmic master clock, diligently counting off the eons for galaxies, stars, and black holes alike?
The truth is, our most fundamental theories of physics begin to fray around the edges when we push this concept too far. On the one hand, we have the macroscopic world, the one we inhabit, where time clearly moves forward, driven by the relentless march of entropy, the universe's tendency toward increasing disorder.
You see a broken cup never reassemble itself, a spilled drink never leap back into its glass. This is time's arrow, clear as day. But then you dip your toe into the bizarre, counterintuitive waters of quantum mechanics, and suddenly the concept of time gets incredibly murky. At the very smallest scales, at the level of subatomic particles, time doesn't seem to play by the same rules.
It's almost as if it ceases to be a fundamental property and becomes something far more ephemeral, something that might even vanish entirely from the equations. Consider the deep scientific mystery that continues to perplex physicists. If time is truly fundamental, why does it behave so differently at different scales? Why does it seem so rigid and unyielding in our everyday experience, yet so fluid, even non-existent in the quantum realm? It's like trying to grasp a handful of water. The harder you squeeze, the more it slips through your fingers. This isn't just an academic exercise. It touches upon the very nature of reality. If time isn't what we assume it is, then our understanding of causality, of past, present, and future, might need a radical overhaul. It's a bit like finding out the ground you've been standing on your whole life is actually a giant, slow-moving conveyor belt. Kinda unsettling, right? The universe might not be clocking in, but rather experiencing an unfolding of events that only appears sequential from our limited perspective. This is where the real fun begins. So you're nestled in, perhaps a bit more thoughtful about that ticking clock on your wall. If time isn't what we thought, then what is it? For centuries, before the mind-bending revelations of the 20th century, time was largely considered an absolute, unchangeable constant, like a giant, invisible metronome for the entire universe. Isaac Newton, the scientific giant whose laws still describe so much of our everyday world, certainly thought so. For him, time flowed uniformly, everywhere, without reference to anything external. It was a backdrop, a stage upon which the cosmic drama unfolded, never affected by the actors or their movements. Easy, straightforward, comforting. But then came Albert Einstein, and with him, a paradigm shift that utterly shattered this comfortable notion. Einstein didn't just tweak Newton's ideas. He revolutionized them, introducing us to relativity and the astonishing concept of space-time. Imagine, if you will, that space and time aren't separate entities at all. Instead, they're woven together into a single four-dimensional fabric, much like a trampoline. When something with mass sits on this trampoline, say a star or a planet, it creates a dip, a curve in the fabric. This curve, we now understand, is what we perceive as gravity. But here's the kicker. This fabric isn't just space. It includes time. What does this mean for our perception of time? It means that time isn't a fixed universal ticking. Instead, it's relative. It can stretch, it can shrink, it can even bend, depending on two primary factors, speed and gravity. This phenomenon is known as time dilation, and it's not science fiction. It's a verifiable, measured fact of our universe. Let's take speed first. Imagine you're on a spacecraft traveling incredibly fast, close to the speed of light. From your perspective, everything feels normal. You're living, breathing, and experiencing time as you always have. But if someone back on a slower moving planet were watching you, they would observe your clock ticking slower than theirs. Your movements would appear sluggish, your words drawn out. And when you returned, you would be younger than your friends and family who remained on Earth. Sounds wild, right? It's been proven with atomic clocks flown on airplanes, which return infinitesimally behind identical clocks that stayed on the ground. The effect is tiny at everyday speeds, but it's there. So, the faster you move through space, the slower you move through time. It's almost as if you're spending your allocated space-time budget and you have to choose how to spend it. Now, let's consider gravity. Remember that trampoline analogy? The deeper the dip, the more gravity is present. And just as gravity warps space, it also warps time. The stronger the gravitational field, the slower time passes. If you were standing on the surface of a neutron star, an incredibly dense object, time would pass significantly slower for you than for someone observing you from a comfortable distance in deep space. In fact, for an astronaut orbiting a black hole, time would crawl to an almost complete stop from an outside observer's perspective, while for the astronaut, moments would still unfold normally. This isn't just theoretical, it's crucially important for technologies like GPS. The satellites orbiting Earth experience slightly weaker gravity and move at different speeds than us on the surface, so their clocks tick at a slightly different rate.
Without constant, precise adjustments based on Einstein's theory of relativity, your GPS navigation would be wildly inaccurate, sending you on a wild goose chase. The profound implication of space-time is that there is no universal now. My now might be different from your now, especially if we're moving at different speeds or experiencing different gravitational pulls. The concept of absolute simultaneity, two events happening at precisely the same moment for everyone, everywhere, simply doesn't hold up in a relativistic universe. This leads to an enduring scientific debate. If now is relative, does a fixed past and future even exist? Some interpretations of relativity suggest a block universe where all of space-time, past, present, and future, exists simultaneously, like a giant, unchanging tapestry. We merely perceive ourselves as moving through it. This challenges our intuitive understanding of free will and causality, doesn't it? It suggests the universe doesn't have a single, unified, what time is it? Because time itself is a highly localized personal experience. It's not a universal river. It's more like countless little streams, each flowing at its own unique pace, influenced by the landscape of space-time around it. You're starting to get a feel for how squishy time can be, aren't you? How it bends and warps with speed and gravity, making the idea of a universal clock seem, well, a bit quaint. But if relativity already makes time feel like a personal, localized experience, prepare yourself, because when we dive into the quantum realm, things get even stranger. Here, at the smallest, most fundamental scales of reality, the realm of atoms, electrons, and photons, the very concept of time seems to unravel, almost as if it's an emergent property rather than an inherent one.
Imagine for a moment trying to describe a quantum particle's journey. You might intuitively think it travels from point A to point B over a certain duration, but in quantum mechanics, the picture gets blurry, fast. Particles don't just follow a single path. They can take all possible paths simultaneously until they are observed. This is part of the mind-bending phenomenon called superposition, where a particle can exist in multiple states at once. If a particle is in multiple places at once and taking multiple paths, how do we even begin to define its time or its speed? It's like trying to time a runner who's running every possible route on the track simultaneously. The deepest mystery here, and a constant source of scholarly debate, revolves around the Schrödinger equation. This fundamental equation describes how quantum systems evolve over time. But here's the kicker, it's perfectly reversible. What does that mean? It means if you know the state of a quantum system now, the equation can tell you its state in the future and its state in the past.
There's no inherent arrow of time built into the core equations that govern the quantum world. Unlike our macroscopic experience where broken cups never spontaneously reassemble, quantum processes can, in theory, run backward just as easily as they run forward.
This is profoundly unsettling, as it suggests that the unidirectional flow of time we perceive might be an illusion that only emerges when countless quantum particles interact and average out their behavior. Think about a single electron. Does it know what time it is? Does it have a tiny internal clock ticking away? According to our best theories, the answer seems to be a resounding no. At its fundamental level, an electron simply exists in a probabilistic state, evolving not through a sequence of discrete moments, but as a wave of possibilities. When we make a measurement, we collapse this wave function, forcing the particle to choose a specific state, a specific location. It's only then that we impose our human concept of a moment upon it. But before that measurement, its existence is, in a sense, timeless. This leads to the fascinating idea that time, as we know it, might not be a fundamental ingredient of the universe, but rather an emergent property. Imagine a bustling city. From above, you see traffic flowing, people moving, a dynamic, ever-changing landscape. But if you zoom in on a single car, or even a single molecule of exhaust, the flow of the city isn't really there. It emerges from the collective behavior of countless individual components. Perhaps time is like that. Perhaps it's an illusion that arises from the vast number of particles and interactions in the universe, an effect of statistical averaging rather than a deep, underlying property. It's like how temperature emerges from the jiggling of countless atoms. No single atom has a temperature.
One of the big challenges in physics is unifying general relativity, which describes gravity and space-time on large scales, with quantum mechanics, which describes the universe at its smallest scales. When physicists try to combine these two incredibly successful theories, time often becomes a problematic variable, sometimes even disappearing from the equations altogether.
This is part of the problem of time in quantum gravity, a deep, unresolved mystery. If a future theory of everything doesn't include time as a fundamental variable, it would dramatically reshape our understanding of reality, suggesting that the universe, in its rawest, most fundamental state, exists in a timeless configuration, and our experience of sequential moments is just how our brains process its complexity. It's enough to make you wonder if your alarm clock is just a very elaborate joke. So, you're now contemplating a universe where time is not only relative, but might even be an illusion at its deepest levels. It's a lot to wrap your head around, isn't it? But let's zoom back out from the quantum foam and look at the grandest scales, the cosmic theater itself. If time is so shifty, how do we even talk about the age of the universe? We say the universe is approximately 13.8 billion years old. How can we possibly put a number on that if time isn't universal? The answer lies in something truly monumental. The universe itself serves as a kind of cosmic clock, specifically through its expansion. Imagine an infinitely stretchy balloon with dots painted on its surface. As you inflate the balloon, the dots move further and further apart, but crucially, no single dot is the center of the expansion. Every dot sees every other dot moving away from it. This is a common, though imperfect, analogy for how the universe expands. All galaxies, on average, are moving away from all other galaxies, and the further away a galaxy is, the faster it appears to be receding from us. This fundamental mainstream science fact, known as Hubble's law, is the bedrock of modern cosmology. We observe this expansion by looking at the light from distant galaxies. As light travels through an expanding universe, its wavelengths get stretched, shifting towards the red end of the spectrum, a phenomenon called redshift. The greater the redshift, the faster the galaxy is moving away, and the further back in time we are looking.
By measuring the rate of this cosmic expansion, astronomers can effectively rewind the tape of the universe. If everything is moving apart, then in the past, everything must have been closer together. If you rewind far enough, you reach a point where all the matter and energy in the observable universe were crammed into an incredibly hot, dense state, the event we call the Big Bang. The time it took for the universe to expand from that initial state to its current size gives us its approximate age, 13.8 billion years. So in a sense, the universe does have a clock, but it's not a ticking second hand. It's the rate at which its fabric stretches and grows. It's like measuring the age of a tree by counting its rings, only on a truly colossal scale.
However, this brings us to an open scientific mystery, a debate that has simmered within cosmology for years: the exact rate of the universe's expansion. We have different methods to measure it. One way is to look at the cosmic microwave background, CMB, the faint afterglow of the Big Bang. This ancient light provides a snapshot of the early universe, allowing us to predict the expansion rate. Another way is to observe distant supernovae, which are incredibly bright exploding stars that act as standard candles, allowing us to measure distances and how fast galaxies are moving away from us right now. Here's the catch. These two methods yield slightly different results for the expansion rate, leading to what's known as the Hubble tension. It's a small difference, but it's significant enough to puzzle scientists. If the early universe and the late universe seem to be expanding at slightly different, seemingly contradictory rates, what does that tell us about the cosmic clock? Does it mean our understanding of the universe's age is slightly off? Or, more profoundly, does it hint at new, undiscovered physics? Perhaps there's something we don't understand about dark energy, the mysterious force accelerating the expansion, or even about gravity itself. It's like having two incredibly precise watches, both supposedly calibrated to the same standard, but one always runs a tiny bit faster than the other.
Which one is right? Or are they both subtly wrong, pointing to a flaw in our understanding of time's cosmic flow? This tension suggests that, while the universe certainly expands, giving us a way to measure its past, the precision of that measurement, and what it might imply about the universe's fundamental knowledge of its own age, is still very much an active area of investigation.
It's a bit like the universe is giving us a puzzle where two pieces almost fit, but not quite, and we're left wondering if we're missing a piece, or if the whole picture is subtly different from what we first imagined.
You're doing great, navigating the strange currents of cosmic time. We've seen how relativity makes time fluid, and quantum mechanics makes it appear to vanish. We've even used the universe's expansion as a kind of grand, albeit imperfect, cosmic clock. But there's another, more intuitive reason why we perceive time moving forward, and it's a concept you've probably encountered without even realizing its profound implications: entropy.
Think about your room. If you don't clean it, what happens? It gets messier, right? Things get scattered, dust accumulates, clothes pile up. This isn't because some mischievous force is actively trying to disorganize your space. It's simply the natural tendency of systems to move from order to disorder.
This fundamental principle is known as the second law of thermodynamics, and it's a cornerstone of mainstream science. It states that in any isolated system, entropy, a measure of disorder or randomness, will always either increase or stay the same. It will never decrease. In simpler terms, things tend to spread out, cool down, and generally become more disorganized over time. This unwavering increase in entropy is widely considered to be the arrow of time. It's the reason why you can't unscramble an egg, unburn a log, or spontaneously put together a shattered teacup. These processes are all driven by entropy increasing. The universe as a whole is one giant isolated system, at least for now, and it's constantly increasing its entropy.
Stars burn out, scattering their energy into space. Galaxies eventually drift apart. Over unimaginable timescales, the universe is expected to become a cold, dark, uniform expanse, a state of maximum entropy known as heat death. So, while relativity tells us how time flows, and quantum mechanics makes us question if it fundamentally exists, Entropy tells us why it flows in one direction, from past to future. Our perception of time's direction is deeply linked to our experience of increasing disorder. If you saw a movie of an egg spontaneously unscrambling itself and jumping back into its shell, you'd instantly know the movie was playing backward. That's your brain instinctively recognizing the arrow of time dictated by entropy. It's a bit like having a cosmic do not rewind sign on the universe's VCR. However, this brings us to a significant open scientific mystery and scholarly debate. How did the universe start with such incredibly low entropy? If the natural tendency is towards disorder, why was the Big Bang, the very beginning of our universe, an incredibly ordered low entropy state? For the universe to have grown to its current complexity, with galaxies, stars, planets, and even life, it must have started from a state of very low entropy, providing the energy gradients necessary for all these structures to form. If the universe started in a high entropy state, it would have been a chaotic, featureless soup, and nothing interesting would have ever happened.
This is often called the past hypothesis, and explaining this initial low entropy state is one of the biggest challenges in cosmology.
Was it a freak statistical fluctuation? Incredibly unlikely, but possible, in an infinite multiverse? Did it arise from an even earlier, more chaotic universe, perhaps one that bounced back from a previous collapse? Some theories suggest that our universe is just one pocket in a larger multiverse, where other regions might have different initial entropy conditions. Others propose that our current understanding of entropy at the very beginning of the universe might be incomplete. It's a head-scratcher, because if entropy always increases, then the most disordered state is the most probable one. So, why did our universe begin in such an improbable, highly ordered state? It's like shaking a box of puzzle pieces and having them spontaneously assemble into a perfect picture. It's the ultimate cosmic lottery win, and understanding how that happened is key to fully understanding time's relentless march forward. The universe knows what direction its internal messy clock is ticking, but we're still figuring out why it was so tidy to begin with. You're settling deeper into the strange scientific landscape of time, aren't you? From the relativity of cosmic speeds to the quantum world's timelessness and the entropic arrow that seems to pull everything forward. Now, let's turn our attention to one of the most extreme, mind-bending phenomena in the cosmos. Objects where time doesn't just bend a little, but practically grinds to a halt. Black holes. These cosmic behemoths are not just incredibly dense. They are ultimate laboratories for testing the fabric of space-time itself. Imagine a star much more massive than our sun. When it runs out of fuel, it collapses under its own immense gravity, crushing itself into an incredibly small, infinitely dense point called a singularity. Surrounding this singularity is an invisible boundary called the event horizon. This is the point of no return. Once anything, even light, crosses the event horizon, it can never escape the black hole's gravitational pull. It's truly a one-way trip. Now, here's where it gets wild for time. Due to their extreme gravity, black holes cause profound time dilation, far more dramatic than anything we've discussed so far. Picture yourself orbiting a black hole, safely outside the event horizon. From your perspective, time would pass normally. You'd check your watch, sip your cosmic coffee, and continue on your way. But if you were observing a brave or foolish astronaut falling towards the event horizon, you would see something truly astonishing. As the astronaut approaches the event horizon, their clock, from your perspective, would appear to slow down dramatically. Their movements would become agonizingly sluggish, their voice drawn out into an impossibly deep, slow rumble. They would seem to freeze, hovering just at the edge of the black hole, never quite crossing over, their light becoming redder and redder until it completely fades out of view. For the astronaut, however, their experience is entirely different. From their perspective, time would continue to flow normally. They wouldn't feel any slowing down. They'd experience the moments rushing by as they plunged toward the singularity, swiftly crossing the event horizon. The terrifying truth is, within a matter of moments for them, they would reach the singularity, likely spaghettified by the intense gravitational tides. So, one person sees time almost stopping, while the other experiences it racing to a violent end. It's a fundamental mainstream science fact, predicted by Einstein's general relativity and continuously supported by observations of black holes affecting the matter around them. It really makes you wonder about the last time you were stuck in a slow-moving queue. At least your time wasn't slowing to a crawl.
This leads to a profound open scientific mystery and ongoing scholarly debate. What happens to time inside a black hole? Once you cross the event horizon, gravity is so strong that the usual dimensions of space and time seem to swap roles. What we consider time, pointing to the future now, points toward the singularity, and what we consider space now becomes the direction of inevitable movement.
Does time cease to exist in a meaningful sense inside the event horizon? Does it become simply another spatial dimension? Or does it end abruptly at the singularity, the point of infinite density? Our current physics breaks down at the singularity, meaning we don't have a complete theory to describe what truly happens there.
Some theories suggest that information, including information about time, isn't truly lost in black holes, but perhaps gets encoded on the event horizon itself, leading to the intriguing concept of the holographic universe. Other theoretical frameworks propose that singularities might be gateways to other universes, or even that they don't truly form due to quantum effects. But for now, the fate of time beyond the event horizon remains one of the universe's most enigmatic secrets. It's a place where our understanding of reality hits a wall, and the concept of a cosmic clock face simply melts away. You're doing remarkably well, journeying into the deep mysteries of time. We've seen its relativistic twists and quantum disappearances, the entropic push forward, and its dramatic slowdown near black holes. But let's rewind even further, to the very beginning of everything, to the early universe.
If time is such a tricky concept now, how did it even begin in those fleeting, furious moments after the Big Bang? Imagine a state of unimaginable density and heat, a singularity from which our entire cosmos burst forth. This is the Big Bang, the widely accepted mainstream scientific model for the universe's origin. In the very first fractions of a second, the universe expanded at an astonishing rate, undergoing a period called inflation. During this cosmic infancy, the laws of physics as we know them were still forming. So, did time itself have a beginning? This is where things get truly philosophical and scientifically profound. According to general relativity, time and space emerged together from the Big Bang. Before that moment, the concept of before itself loses meaning. It's not that there was a time before time that we simply can't access. It's that time, as a dimension, simply didn't exist in the way it does now. It's like asking what's north of the North Pole. The concept just doesn't apply. So, in this view, the universe didn't start in time. Time started with the universe. The entire fabric of space-time unfolded from that initial cosmic event. This is a fundamental concept in modern cosmology, providing a framework for understanding how galaxies, stars, and ultimately, us, came to be. However, this leads directly to a profound, open scientific mystery and a subject of intense scholarly debate. What actually caused the Big Bang, and what precisely was the nature of time at that absolute earliest instant? Our current laws of physics, particularly general relativity, break down at the singularity of the Big Bang, just as they do at the singularity inside a black hole. We simply don't have a theory that can accurately describe that initial moment of infinite density and temperature. This is the realm where quantum mechanics and gravity must finally be united into a theory of quantum gravity, which we currently lack. Some theories, like loop quantum gravity, suggest that space-time itself might be quantized, meaning it's made up of tiny, discrete chunks, rather than being a smooth continuum. In such a model, the Big Bang might not have been a true singularity, but rather a quantum bounce from a previous contracting universe. If so, time wouldn't have had a beginning in the traditional sense, but would have flowed continuously through multiple cycles of expansion and contraction, like a cosmic accordion. This would mean that the universe always knew what time it was, even if it was just flowing through an earlier iteration of itself. Sounds a bit like a cosmic reboot, doesn't it? Other hypotheses, such as those arising from string theory, propose entirely different scenarios for the birth of the universe, where the Big Bang might have been the collision of higher dimensional brains or membranes. In these models, the concept of time's beginning could be radically different, perhaps emerging from a higher dimensional reality. The question of whether time truly had a first moment, or if it always existed in some form, even before our universe as we know it, remains one of the deepest unresolved questions in physics. We talk about the universe being 13.8 billion years old, but that's really 13.8 billion years since the universe became something we can describe with our current physics. What was happening before that, or if before even makes sense, is still the ultimate cosmic riddle. It's like arriving at a movie halfway through and wondering how the story began. You can guess, but you don't have all the information. You're doing brilliantly, journeying through the deepest cosmic questions about time. We've explored its strange behavior from the Big Bang to black holes, but a persistent and perhaps the most challenging problem in theoretical physics is trying to unite the two pillars of modern science, general relativity and quantum mechanics. And when physicists attempt this grand unification, a truly unsettling thing often happens. Time seems to disappear from the most fundamental equations. This is the heart of the problem of time in quantum gravity. Remember how general relativity describes gravity as the curvature of space-time on large scales, dictating how planets orbit stars and how the universe expands? And recall how quantum mechanics governs the bizarre world of particles, probabilities, and superposition at the tiniest scales? Both theories are incredibly successful within their own domains, providing remarkably accurate predictions. The issue arises when you try to apply quantum principles to gravity itself, or when you attempt to describe the universe at moments when both extreme gravity and quantum effects were dominant, like the very early universe or inside black holes. The leading candidate for a theory of quantum gravity, one that aims to reconcile these two giants, is often sought through approaches like string theory or loop quantum gravity. And here's the kicker. In many of these theoretical frameworks, particularly in canonical quantum gravity, when you write down the equations that describe the universe at its most fundamental level, the variable for time simply drops out. It's like trying to describe a symphony, but finding that the concept of rhythm or tempo is entirely absent from your musical notation. This is a mainstream scientific challenge, a profound stumbling block that has perplexed physicists for decades. The most famous example is the Wheeler-DeWitt equation, a foundational equation in canonical quantum gravity, which contains no time variable.
It describes a static, unchanging universe, a frozen formalism. This leads to a staggering, open scientific mystery and intense scholarly debate. If time isn't a fundamental variable in the equations that describe the universe at its most basic level, then is it truly fundamental at all? Could time, as we perceive it, be an emergent phenomenon, something that arises from the collective behavior of countless fundamental,
Timeless interactions? It's a bit like watching a movie. From your perspective, there's a clear sequence of events unfolding over time, but the movie itself is just a series of static images, frames, projected one after another. No single frame contains time. Time emerges from their rapid succession.
Perhaps our universe is like that, a collection of nows that only appears to flow because of how our brains process information.
Some physicists argue that time is merely a measure of change. If nothing ever changed in the universe, would there be any time? Perhaps not. If the fundamental equations are timeless, then the universe might be viewed as a timeless block, where all configurations exist simultaneously, and our perception of time is simply our way of navigating through this unchanging whole. Others suggest that the time that disappears from these equations is simply our human-centric classical notion of time, and that a deeper, more fundamental concept of quantum time exists, waiting to be discovered. It's a bit like searching for a specific key, only to find the entire lockbox has vanished. The implications are enormous. If time is not fundamental, then concepts like cause and effect, free will, and even the very meaning of evolution become far more complex. It would mean the universe, in its rawest, most profound essence, doesn't know what time it is, because time itself isn't part of its core identity. We are the ones imposing a clock onto a universe that might simply be. It's a wonderfully unsettling thought, isn't it? That our most deeply ingrained sense of progression might be a grand cosmic illusion, and the universe is simply existing timelessly.
You're well on your way to becoming a true time traveler of the mind, traversing the perplexing landscapes where time shifts, blurs, or simply vanishes. Now, let's indulge in a classic science fiction staple that perpetually fascinates us: time travel. If time is as malleable and mysterious as our previous sections suggest, can we ever truly traverse it? The concept of time travel, specifically to the past, is a deeply ingrained part of our popular culture, conjuring images of DeLorean cars and phone booths. But in the realm of mainstream science, it's a far more complex and often contradictory idea. General relativity, in its wilder solutions, does permit some forms of time travel, or at least structures that could theoretically allow it. For instance, the theory allows for closed time-like curves, CTCs. Imagine space-time bending back on itself like a loop. If you could follow such a loop, you would eventually return to your starting point in both space and time, essentially arriving back before you left. This is a fascinating theoretical possibility. One hypothetical mechanism for creating CTCs involves wormholes, often visualized as shortcuts through space-time, connecting two distant points in space and time. Think of folding a sheet of paper and poking a hole through it. The hole connects two points that were far apart on the flat sheet. If one end of a wormhole were subjected to extreme gravitational time dilation, perhaps by being near a black hole, or moved at relativistic speeds, it could theoretically become a time machine. Another theoretical avenue involves exploiting the immense gravity of spinning black holes, which could, in certain configurations, warp space-time sufficiently to allow for CTCs. These are all theoretical solutions derived from Einstein's equations. They are not observed phenomena, nor do we have any practical way of creating them. It's a bit like having the blueprints for a fantastical palace, but no way to gather the materials or construct it.
However, This brings us face to face with a massive open scientific mystery and scholarly debate: the paradoxes of time travel. The most famous of these is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, how could you then exist to travel back in time in the first place? This kind of logical inconsistency suggests that true, unrestricted time travel to the past might be impossible. Physicists grapple with various potential resolutions to these paradoxes. One popular idea is the Novikov self-consistency principle, which suggests that if time travel were possible, any actions a time traveler took in the past would be self-consistent with the future they came from. In this view, you could try to kill your grandfather, but something would inevitably prevent you, ensuring causality remains intact. You'd trip, or the gun would jam, or you'd just get a sudden urge for a coffee break. The universe would find a way to stop you from creating a paradox. Another speculative solution comes from the multiverse theory. Perhaps every act of time travel doesn't change your past, but instead creates a new parallel universe or timeline. So, if you went back and changed something, you would simply branch off into a new reality, leaving your original timeline untouched. In this scenario, you wouldn't be erasing your existence, just creating an alternate version of reality where you never existed. It's a neat way to sidestep the paradoxes, but it requires an infinite number of parallel universes, which is quite the cosmic commitment. The current consensus in mainstream physics leans towards the idea that time travel to the past, if not outright impossible, is at least extraordinarily unlikely or restricted by mechanisms we don't yet understand. The universe seems to have a built-in resistance to violating causality. While traveling forward in time is demonstrably possible, just travel fast or go near a black hole, and you'll experience it. Reversing the arrow of time appears to be a much tougher, perhaps insurmountable challenge. It's almost as if the universe knows what time it is, and it's quite adamant about keeping its past in the past.
You've bravely navigated some of the most complex concepts in physics regarding time. From the relativistic warp to quantum timelessness, and even the paradoxes of time travel. But let's bring it closer to home, inside your very own body. Does your personal sense of time, that steady internal rhythm, align with the grand cosmic clock, or is it another one of those curious illusions? We're going to explore biological rhythms and perception.
It's a mainstream scientific fact. Your body is a marvel of internal clockwork. You have a circadian rhythm, a roughly 24-hour cycle that governs your sleep-wake patterns, hormone release, body temperature, and many other physiologichical processes.
This rhythm is primarily synchronized by light cues from your environment, specifically by a small region in your brain called the suprachiasmatic nucleus, SCN. It's why you feel tired at night and alert during the day. Even if you were stuck in a cave without any external time cues, your body would still try to maintain this approximate 24-hour cycle.
Think of it as your body's personal grandfather clock, ticking away, trying its best to keep you on schedule.
Beyond the daily cycle, you have other biological rhythms. Your heart beats at a relatively consistent rate. Your breathing follows a rhythm, and even your brain waves exhibit oscillating patterns. These internal clocks are crucial for your survival and well-being. They coordinate the thousands of chemical reactions and biological processes that allow you to function.
So, in a very real sense, your body does know what time it is, or at least it knows what time it should be for its own internal operations. It's a fantastic example of complex biological systems self-organizing around the external environment's dominant rhythm. It's almost like your cells are constantly whispering, "Is it time for coffee yet?" However, this brings us to an open scientific mystery and a fascinating area of scholarly debate: How does your subjective perception of time relate to these objective biological clocks and to the cosmic time we've been discussing? You've undoubtedly experienced how time seems to stretch or shrink depending on the circumstances. A thrilling moment might fly by in what feels like seconds, while a boring lecture can drag on for what feels like an eternity. This phenomenon, known as time perception distortion, highlights that your brain doesn't just passively read a cosmic clock. Instead, it actively constructs your experience of time.
Why does this happen? The exact neural mechanisms are still being explored, but several theories exist. One idea is that our perception of time is linked to the amount of information our brains process. When you're in a novel or exciting situation, your brain processes a lot of new information, leading to the feeling that time is slowing down, or that more moments are being packed into a given duration. Conversely, in routine or boring situations, less information is processed, making time seem to speed up.
Another theory suggests that our perception of time is tied to our emotional state and level of arousal. Fear, for example, can trigger a cascade of neurochemicals that make events seem to unfold in slow motion, allowing for more detailed processing of a threatening situation. It's like your brain shifts into a high frame rate recording mode. Consider also the phenomenon of flashbulb memories, where emotionally significant events seem to be remembered with incredible clarity, almost as if time stood still. This isn't necessarily because time did stop, but because the brain deeply encodes every detail of that moment. So, while your cells follow precise biological rhythms, your conscious experience of time is fluid, elastic, and deeply personal. The universe might be expanding at a certain rate, and atoms might be oscillating in a timeless quantum dance, but your brain is busy creating its own unique narrative of past, present, and future, one that can speed up, slow down, or even skip a beat entirely. It's a reminder that even our most fundamental perceptions are intricately tied to the complex machinery inside our own heads, making the universe's true clock a concept far removed from our subjective tick-tock.
You're truly a seasoned cosmic explorer by now, aren't you? You've wrestled with time's slippery nature, from the grand cosmic dance to the intimate rhythms within your own skull. We just touched on time travel, specifically the past, and the headaches it causes with paradoxes.
Now, let's drill down into that most famous of paradoxes, the one that makes you question causality itself, the grandfather paradox.
This is a classic and frequently debated scenario in physics and philosophy, a true mainstream scientific consideration when discussing the possibility of past time travel.
The paradox states that if you were to travel back in time and prevent an event that was crucial to your own existence, most famously, if you were to prevent your grandfather from meeting your grandmother, then you would never have been born. But if you were never born, then you couldn't have traveled back in time in the first place. See the logical knot? It's a bit like trying to build a bridge that collapses before you can even cross it to get to the other side to build it. It's an immediate, head-spinning contradiction that seems to make time travel to the past utterly impossible.
The grandfather paradox and its many variations, like preventing the discovery of something vital for your time machine's existence, highlights a fundamental problem with causality. In our everyday world, cause always precedes effect. A ball hits a window, then the window breaks. Time flows forward, and events unfold in a strict sequence. Time travel to the past, however, seems to threaten this fundamental order by allowing an effect to happen, your intervention in the past, that then negates its own cause, your existence. It's a delightful little thought experiment that keeps physicists awake at night. This very directly leads to a profound open scientific mystery and a highly active area of scholarly debate. How does the universe, if time travel were possible, avoid such logical contradictions? No one has observed a time traveler creating a paradox, which leads many physicists to believe there must be a mechanism that prevents them.
One prominent hypothesis, as we touched upon earlier, is the Novikov self-consistency principle. This principle, named after Russian astrophysicist Igor Novikov, proposes that if time travel to the past is possible, then only self-consistent timelines are allowed. Any attempt to change the past would be automatically thwarted by events or circumstances, ensuring that no paradoxes are created. It's not about fate in a mystical sense, but rather that the laws of physics themselves would conspire to prevent a contradiction. If you tried to shoot your grandfather, the gun would misfire, or someone would bump your arm, or you'd suddenly sneeze. The universe would simply not allow the paradoxical event to occur.
This interpretation suggests that while you might have free will in your choices, the outcome of those choices would be constrained by the need for a consistent timeline. You could try, but you'd fail, perhaps in a comically improbable way. Another fascinating, albeit more speculative solution comes from the many worlds interpretation of quantum mechanics. In this view, whenever a quantum event occurs, the universe splits into multiple parallel universes, each representing a different outcome. Applied to time travel, if you went back and changed the past, you wouldn't be altering your original timeline. Instead, you would simply be branching off into a new parallel universe where your actions create a different history. Your original universe remains untouched, and the you who traveled back would effectively create a new you in the new timeline. This elegantly bypasses the paradox. You exist because you came from a different original timeline, and your actions in the past simply create a new reality, leaving the old one intact. This is a very intriguing way to resolve the paradox, though it comes with the cost of assuming an incredibly vast number of parallel realities. Ultimately, the grandfather paradox is a compelling argument for why time, as we perceive it, likely has a fixed, unalterable past. The universe, in its intricate cosmic dance, seems to know exactly what time it is, and it's not keen on letting anyone mess with its history. It's almost as if the universe is quietly enforcing its own no-rewind policy. You're truly a seasoned cosmic explorer, gracefully navigating the intricacies of time, from its quantum ambiguities to the perplexing grandfather paradox. If the idea of preventing a paradox through self-consistency doesn't quite sit right, then let's explore a concept that offers a more expansive, almost fantastical, escape hatch: the multiverse and parallel timelines. The concept of a multiverse is a truly mind-bending idea in mainstream theoretical physics. It suggests that our universe isn't the only one, but rather one among an enormous, possibly infinite number of other universes. These aren't just distant regions of our own cosmos. They are entirely separate realities, each with its own set of physical laws, initial conditions, and unfolding history. It's like a colossal cosmic collection of bubbles, and each bubble is a complete universe. This isn't just pure speculation. Various theoretical frameworks in physics naturally lead to the idea of a multiverse. For instance, the theory of cosmic inflation, which describes the rapid expansion of the early universe, suggests that inflation might never truly end everywhere, perpetually spawning new bubble universes. Another avenue is the many worlds interpretation of quantum mechanics, which we briefly touched on earlier. The many worlds interpretation is a significant open scientific mystery and a subject of intense scholarly debate. It posits that every time a quantum measurement is made, or every time there's a probabilistic event, the universe splits or branches into multiple parallel universes, each representing a different possible outcome.
So, If a photon can be polarized horizontally or vertically, in one universe it's horizontal, and in another it's vertical. This happens constantly, an infinite number of times every second, creating an ever-diverging tree of realities. It's a rather elegant, and terrifying perhaps, way to resolve the quantum measurement problem, but it requires accepting the existence of an unimaginable number of parallel timelines, each playing out a slightly different version of reality. How does this relate to time and its perception? In the context of time travel, especially concerning paradoxes like the grandfather paradox, the multiverse offers a compelling, albeit speculative, resolution. If you were to travel back in time and change an event crucial to your existence, you wouldn't be altering your original timeline. Instead, your actions would cause a branching event, creating a new parallel timeline where that change occurs. You, the time traveler, would then exist in this new timeline, while your original timeline continues on its merry way untouched. So, in this view, you haven't prevented your own birth in your original universe. You've simply created a new universe where you were never born, and you're now stuck in it. Phew. No paradoxes, just parallel realities. It's like a choose-your-own-adventure book, where every choice takes you down a new path.
This concept also touches on the idea of different time flows in parallel universes.
Could there be universes where time flows backward? Or where it moves in discrete, jerky steps, rather than a smooth continuum? While most multiverse theories assume similar fundamental laws, including the direction of time due to entropy, it's not entirely ruled out that some universes might have unique temporal properties.
The debate here isn't just about whether other universes exist, but also about the extent of their diversity. Could they know what time it is in a fundamentally different way? The implications are profound. If every possible outcome of every decision creates a new universe, then every what-if scenario you've ever pondered has already played out somewhere in some parallel reality.
This means the universe doesn't have a single "what time is it?" but rather an infinite chorus of "what time is it now?" each in its own unique unfolding reality. It makes our own little pocket of space-time feel both incredibly special and utterly insignificant all at once.
You're truly a seasoned cosmic explorer, gracefully navigating the intricacies of time, from its quantum ambiguities and the perplexing grandfather paradox to the concept of the multiverse. Now, let's consider a more abstract, yet profoundly significant aspect of the universe's temporal nature: information and time's flow. Does the universe's information content define its passage, or perhaps even give rise to it? Think about information not just as facts or data, but as the fundamental arrangement of matter and energy. Every particle, every interaction, every pattern in the cosmos can be considered a form of information. For instance, the exact position and momentum of every atom in your coffee cup is information. A mainstream science fact is that information is never truly destroyed, only transformed. This is related to the laws of thermodynamics, particularly the idea that the total information in an isolated system remains constant or increases. This brings us back to our old friend, entropy. Recall that entropy is a measure of disorder. It can also be understood as a measure of the missing information about a system's precise state. If a system is highly ordered, like a perfectly arranged set of dominoes, you have a lot of information about its specific configuration.
If those dominoes are scattered randomly, you have less specific information about their precise arrangement. The entropy is higher. As entropy increases, the universe moves towards a state where information is more diffuse, less concentrated, and harder to retrieve specific details from. This relentless spread of information, or rather, the loss of useful information, is what many physicists propose gives time its arrow. It's like watching a perfectly crisp photograph slowly blur and fade over the centuries. The image itself, the information it contains, is becoming less distinct.
This leads to a fascinating open scientific mystery and scholarly debate. Is time itself fundamentally tied to the processing or changing of information? Some theoretical physicists propose that time isn't a fundamental dimension like space, but rather an emergent property arising from changes in the universe's information content.
In this view, if nothing in the universe ever changed, if no information was ever processed or rearranged, then time, in a meaningful sense, would simply cease to exist. Time, then, would be inextricably linked to the universe's ongoing computations, its ceaseless reordering of information. Consider the universe as a gigantic, incredibly complex computer. Every interaction between particles, every chemical reaction, every star burning, could be seen as a computation that changes the state and arrangement of information. The flow of time would then be the progress of this cosmic computation.
This perspective suggests that the universe knows what time it is because its internal state is constantly being updated and processed, moving from one informational configuration to the next. The direction of time's flow forward would be dictated by the irreversible nature of information spreading out, akin to how information gets blurred when you mix paints.
You can't unmix them perfectly to get back the original distinct colors. Another angle on this debate is the concept of quantum information. At the quantum level, information behaves in incredibly peculiar ways, often entangled across vast distances. Some theories explore whether the collapse of a quantum wave function, the moment a probabilistic quantum state becomes a definite one, is an information processing event that contributes to the emergence of time. If every such collapse creates new information or resolves uncertainty, then perhaps the very fabric of time is woven from these tiny informational updates. It's a subtle point, but the universe might not have a clock so much as it is a clock, defined by its ceaseless informational dance. It truly turns your understanding of what a tick even means upside down.
You're navigating the deep currents of cosmic time like a seasoned voyager, pondering everything from its quantum disappearance to its informational essence. We've explored external factors influencing time, but now let's turn inward to the most immediate and personal experience of time, the flow of consciousness. Your subjective perception of time is unique, but how objective is it really? It's a mainstream scientific fact that your brain constructs your reality, including your experience of time. What you perceive as a seamless flow from one moment to the next isn't necessarily a direct readout of a universal clock, but rather a complex, dynamic process of neural activity. Think of how your brain processes sensory information, sights, sounds, smells. It doesn't just receive raw data. It interprets, organizes, and stitches it together into a coherent narrative. Time perception is no different. Your brain is constantly making predictions about the future, comparing them to the present, and integrating them with memories of the past. This intricate dance of neural networks creates your conscious awareness of now and its progression. It's truly incredible, isn't it? Your brain isn't just a receiver, it's an active editor, shaping your temporal experience. This leads to a profound open scientific mystery and a lively scholarly debate. Is the now that you experience truly objective, or is it merely an artifact of your cognitive processes? If time is merely an emergent property, or if the universe itself is fundamentally timeless, then our perception of a distinct, flowing present moment becomes a fascinating puzzle. Different philosophical and scientific theories offer various perspectives.
One viewpoint, often called presentism, argues that only the present moment is real. The past is gone, and the future has not yet arrived. This aligns with our everyday experience, where we feel ourselves constantly moving through a distinct now. However, this view clashes with the implications of Einstein's relativity, where, as we discussed, simultaneity is relative, meaning two events that are simultaneous for one observer might not be for another. If now is relative, then whose now is the real now? It's like everyone in a race claiming to be in first place, but they're all running at different speeds. Another perspective, eternalism, or the block universe theory, suggests that all moments in time, past, present, and future, exist simultaneously, like frames in a film reel. We simply experience them sequentially as our consciousness moves through this fixed block of space-time. In this view, your now is just a specific slice of this pre-existing reality, and your feeling of time flowing is an illusion of your consciousness. This idea, while challenging to our intuition about free will, is more consistent with the relativistic nature of time. It implies that the universe does know what time it is, in a static, all-encompassing way, but our subjective experience is one of unfolding. Furthermore, consider the intriguing phenomenon of attention and perception. When you focus intensely on a task, time can seem to fly by. When you're bored, it drags. Some research suggests that our perception of duration is linked to how much attention we allocate to time itself or to the events occurring. If your attention is diverted, you might perceive less time has passed. This highlights that your brain is actively sculpting your temporal experience, often without your conscious awareness. So, while the cosmic clocks might tick at some fundamental rate or not at all, your internal experience is a beautifully intricate and sometimes deceptive construction. The universe might simply be, but your consciousness is busy narrating its grand story, second by second, or so it seems. You're truly a seasoned cosmic explorer, gracefully navigating the intricacies of time from its quantum ambiguities, the perplexing grandfather paradox, the concept of the multiverse, and the very flow of consciousness. Now, let's shift gears slightly and marvel at a truly astonishing discovery that blurs the lines between science fiction and reality, giving us a tangible glimpse into new ways the universe might keep time. Time crystals. This is a groundbreaking mainstream science fact that was theorized in 2012 by Nobel laureate Frank Wilczek and then experimentally observed in 2017. You're familiar with regular crystals, right? Like a diamond or a snowflake? These are structures where atoms are arranged in a repeating pattern in space. For example, the carbon atoms in a diamond repeat in a precise three-dimensional lattice. They are stable, low-energy configurations. Now, imagine a material where the atoms don't just repeat in space, but also in time. This is the essence of a time crystal. A time crystal is a phase of matter that has a spontaneous repeating motion in time, even when it's in its lowest energy state. Think of it like a jello jigging indefinitely, without any external prodding, or a clock that ticks forever, without needing to be wound. This is utterly bizarre because, according to our standard understanding of physics, systems in their lowest energy state, their ground state, should be perfectly still, exhibiting no motion. Yet, time crystals inherently oscillate, breaking time translation symmetry. The idea that the laws of physics are the same at all times. It's like discovering a perpetual motion machine, but one that's fundamentally allowed by the rules of quantum mechanics. This phenomenon is distinct from regular oscillating systems, like a pendulum. A pendulum needs energy input to keep swinging, and it eventually slows down due to friction. A time crystal, however, continues its periodic motion without losing energy, even at its coldest, most stable state. The atoms within it are constantly in motion, repeating a specific pattern in time,
without any energy dissipation. It's as if they've found a loophole in the energy laws, allowing them to eternally dance. Researchers have created these remarkable structures using various quantum systems, like chains of trapped ions or defects in diamonds, cooling them to near absolute zero.
It makes you wonder if your old wind-up alarm clock isn't just a basic mechanical device, but secretly yearns to be a quantum time crystal, ticking away for eternity on its own.
This groundbreaking discovery immediately leads to a significant open scientific mystery and an ongoing scholarly debate. What are the full implications of time crystals, and could they offer insights into the fundamental nature of time itself? While current time crystals are tiny and operate at quantum scales, their existence challenges our intuitive understanding of how energy, time, and matter interact. If matter can spontaneously break time translation symmetry, what does that tell us about the universe's inherent temporal properties? Some physicists speculate that time crystals could pave the way for new forms of quantum computing, acting as ultra-stable quantum memories. Others wonder if they could provide clues about a more fundamental quantum clock that underpins the universe, or if our macroscopic experience of time's flow is somehow an emergent property of countless tiny time crystals interacting.
Could the universe, at a deeper level, be made up of these tiny, self-oscillating components, and our sense of linear time is just a grand average of their collective ticking? It's a very speculative idea, but it highlights how even the most basic components of reality might possess inherent temporal characteristics we are only just beginning to comprehend.
The universe might not know what time it is in a conscious sense, but its very building blocks might be capable of a spontaneous, internal, temporal rhythm we're only just starting to detect. You're doing wonderfully, diving deep into the weird and wonderful world of cosmic time. From the Big Bang to black holes, the quantum realm, and even the self-oscillating marvels of time crystals, you've seen how tenuous our grip on time can be. Now, let's confront one of the most intellectually stimulating and challenging ideas in modern physics, the concept of emergent time theories. This perspective suggests that time isn't a fundamental dimension of reality, but rather something that arises from something else, something more basic and perhaps even timeless. The prevailing view in classical physics, going back to Newton, was that time was a fundamental, absolute background against which all events unfolded. Then Einstein came along and wove time into the fabric of space-time, making it relative but still fundamental.
However, when physicists try to marry general relativity with quantum mechanics, particularly in the quest for a theory of quantum gravity, time often becomes a problematic variable, as we discussed with the Wheeler-DeWitt equation. This breakdown at the deepest levels has led many to question time's fundamental status.
This is a significant open scientific mystery and a subject of intense scholarly debate. If time isn't fundamental, what does it emerge from?
One prominent idea is that time emerges from entanglement. Entanglement is a bizarre quantum phenomenon where two or more particles become linked in such a way that they share the same fate, no matter how far apart they are.
Measuring the state of one instantly tells you the state of the other, as if they're communicating faster than light, though no information is actually transmitted in a way that violates relativity. Some theoretical physicists, such as Don Page and William Wooters, proposed a model where observers within an entangled universe could perceive time even if the global universe state was static.
In this view, time emerges from the changing correlations between entangled subsystems. It's a bit like watching a series of dominoes fall. No individual domino knows what time it is, but the sequence of their entanglement creates a perceived flow. Another leading concept suggests that time emerges from thermodynamics and the increase of entropy. As we discussed, the second law of thermodynamics states that disorder, entropy, always increases in an isolated system.
This irreversible arrow of increasing disorder is what gives time its direction.
In this view, time isn't an independent dimension. It's simply a measure of the universe's increasing messiness. If the universe somehow reached a state of maximum entropy, a state of ultimate disorder where nothing more could change, then time, in a meaningful sense, would cease. There would be no more before or after, because there would be no more change to track.
This is a mainstream scientific idea, rooted in the very fabric of our universe's behavior. It's like when your kid's room gets so messy that you can't tell when they started making it messy anymore. It's just perpetually chaotic.
A more radical idea posits that time emerges from information. This builds on the idea that the universe is constantly processing and rearranging information. Every interaction, every measurement, every bit of change can be seen as an informational update. Time, then, is the perceived progression of these informational transformations.
This aligns with the it from bit philosophy, suggesting that information is more fundamental than matter or energy. If time emerges from the processing of information, then the universe knows what time it is, in the same way a computer knows what time it is by executing its operations. It's not an external clock, it's an internal calculation. These emergent time theories offer compelling ways to reconcile the seemingly timeless nature of fundamental quantum equations with our everyday experience of a flowing past, present, and future. They suggest that the universe, in its deepest reality, might not be running on a clock at all, but rather exhibiting changes from which we infer the existence of time.
It's a truly humbling thought. The very fabric of our temporal reality might be nothing more than a grand cosmic illusion, albeit a very convincing and persistent one.
You're doing wonderfully, grappling with the truly profound notions of emergent time. If time isn't fundamental, but instead arises from entanglement or entropy or information, then what does that imply about the very nature of our universe? This leads us to one of the most speculative, yet incredibly intriguing ideas in theoretical physics, the holographic principle.
The holographic principle is a mainstream scientific concept, albeit a theoretical one, that emerged from the study of black holes and quantum gravity. It suggests that all the information contained in a three-dimensional volume of space can be encoded on a two-dimensional surface at its boundary, much like a hologram. Think of a credit card with a holographic image on it.
The 2D image contains all the visual information of a 3D object. In the same way, the holographic principle proposes that our entire three-dimensional universe, with all its matter, energy, and space-time, might just be a projection of information residing on a distant two-dimensional boundary.
It's a bit like living inside a gigantic cosmic movie screen, where everything you perceive as solid and real is actually a shadow or a projection from a flat surface far, far away.
The initial inspiration for this principle came from the work of physicists Jacob Bekenstein and Stephen Hawking on black hole thermodynamics. They discovered that the entropy of a black hole, its measure of disorder or information content, isn't proportional to its volume, but to the area of its event horizon. This was a radical departure from what we intuitively expect.
If information is related to entropy, and black holes contain an immense amount of information, then the fact that this information is scaled by the surface area rather than the volume suggested a deep connection to holography. This observation formed the bedrock of the holographic principle. The maximum amount of information in a region of space is determined by its boundary area, not its volume.
This brings us to a mind-bending open scientific mystery and an ongoing scholarly debate. If our universe is a hologram, how does time fit into this picture? If reality is fundamentally a 2D projection, then how do we perceive a dynamic, evolving 3D universe with a flowing past, present, and future?
One of the leading ideas is that time itself might be an emergent phenomenon within the holographic projection. If the underlying reality is a timeless, information-packed 2D surface, then the perceived flow of time in our 3D experience could arise from the way this information is read or processed.
It's like watching a flat image on a TV screen, where the rapid refresh rate creates the illusion of smooth motion and unfolding events. The TV screen itself doesn't inherently contain motion. It's the sequence of static images displayed over time that creates the dynamic experience. Another facet of this debate explores whether our very perception of time's direction, the arrow of time, is tied to the way information is projected from the boundary. As information on the 2D surface evolves, perhaps it creates the illusion of increasing entropy and the passage of time in our perceived 3D reality. This would mean that the universe doesn't know what time it is in a fundamental ticking sense, but rather that time is a feature of its projected reality.
It's an incredibly abstract idea, but it offers a powerful framework for thinking about the fundamental constituents of reality, potentially reconciling quantum mechanics and general relativity by proposing that gravity itself, and thus space-time, isn't fundamental, but arises from this lower dimensional information. It's like finding out the entire symphony you're listening to is just an incredibly clever arrangement of vibrations on a drum skin, and the feeling of time passing is merely the sequence of those vibrations. You've plunged deep into the mind-bending concepts of cosmic time, from its potential emergence to the idea of our universe as a grand hologram. Now, let's bring it back to a more human scale, examining the fascinating contrast between our meticulously crafted digital time and the vast, enigmatic nature of cosmic time. How do our human measurements stack up against the universe's own scales? It's a mainstream scientific fact that our modern world runs on incredibly precise timekeeping. We're talking about atomic clocks, which are the most accurate timekeeping devices known to humanity. These clocks don't rely on the swing of a pendulum or the rotation of the Earth. Instead, they measure time by counting the extremely stable oscillations of atoms, most commonly cesium atoms, as they jump between energy levels. 1 second is officially defined as exactly 9,192,131,170 oscillations of a cesium atom. These clocks are so precise that they would lose or gain only about 1 second in 100 million years.
This incredible accuracy is vital for global technologies like GPS, which, as we noted earlier, needs to account for relativistic time dilation, but also for synchronized communication networks, financial transactions, and scientific experiments. So, in our daily lives, we've achieved a remarkable degree of precision in measuring what time it is.
It's like having a stopwatch that's virtually perfect. However, this precision in digital time stands in stark contrast to the vast, often ambiguous, scales of cosmic time. We talk about the universe being 13.8 billion years old, or about events happening billions of years ago. These are immense durations, far beyond any human comprehension or direct experience.
And as we've explored, even these large-scale measurements are subject to cosmic uncertainties, like the Hubble tension. The universe doesn't have a single, perfectly calibrated atomic clock at its center ticking away for all to hear. Its time is defined by its expansion, its increasing entropy, and the peculiar behaviors of gravity and quantum particles. It's an open scientific mystery and a subject of ongoing scholarly debate. Is our highly precise, digitally measured time truly capturing the essence of cosmic time, or is it merely a convenient approximation for a much more complex, perhaps non-linear, underlying reality? Consider the challenges of synchronizing clocks across vast cosmic distances. Due to relativity, two observers in different gravitational fields, or moving at different speeds, will experience time differently. There's no absolute simultaneous moment across the entire universe. Our digital clocks, while incredibly accurate locally, cannot account for this cosmic relativity without complex calculations. So, while your phone might show you the exact second, that second might stretch or shrink depending on where you are in the universe and how fast you're moving. It's like everyone in a different country setting their watches to local time, but then wondering why they aren't all synchronized with some theoretical global time. Furthermore, if time is an emergent property, as some theories suggest, then our atomic clocks are simply measuring a symptom of change, rather than a fundamental dimension. They are meticulously counting oscillations that occur over time, but they aren't necessarily tapping into time itself at its deepest level.
It's like measuring the speed of a flowing river with a paddle wheel. You're measuring the effect of the flow, but not the inherent riverness of the water itself. This debate questions whether our most precise human measurements of time are truly universal or merely highly refined approximations based on our limited macroscopic perception. The universe doesn't consult our atomic clocks. It simply unfolds according to its own vast, peculiar rhythms, sometimes in ways that defy our neat digital tick-tocks. You're nearing the end of our cosmic journey through time, a seasoned explorer of its many enigmas. We've seen how time is relative, perhaps emergent, and how our human attempts to quantify it are incredibly precise, yet fundamentally distinct from the universe's own rhythms. Now, let's ponder a profound intersection: fate, free will, and time. Does time's direction dictate our choices, or do our choices shape time? This question delves into the very core of human existence and its relationship with the universe's temporal structure. The concept of free will is our intuitive belief that we have agency, that we make genuine choices that influence the future. You decide to have another sip of your cosmic coffee, or to pull your blanket up higher. These feel like uncoerced decisions. This belief in free will is a cornerstone of our legal systems, moral codes, and personal responsibilities. It's a deeply ingrained human experience, a mainstream psychological and philosophical understanding of how we interact with the world. However, this intuitive sense of free will often bumps up against certain scientific and philosophical interpretations of time. If, for instance, the block universe theory, which is consistent with general relativity, is true, then all of space-time, past, present, and future, already exists as a fixed, unchanging four-dimensional block. In this view, your future choices are already there, laid out in the cosmic tapestry, just as your past choices are. We merely experience them sequentially. This doesn't necessarily mean fate in a mystical sense, but it does suggest that the future is, in some sense, already determined, even if we are unaware of it. It's like watching a movie where all the scenes exist simultaneously on the film reel, and your consciousness is simply playing through them. This raises a significant open scientific mystery and an ongoing scholarly debate. How can free will exist in a universe where the future might already be set? One perspective is determinism, the idea that every event, including every human choice, is causally determined by an unbroken chain of prior occurrences. If the universe's initial state and the laws of physics are all that's needed to predict every subsequent event, then free will might be an illusion. If time simply unfolds as a consequence of these predetermined states, then our choices are merely the inevitable outcome of a vast cosmic calculation. It's like a super complicated set of dominoes, where pushing the first one means all the others will fall in a specific sequence.
However, other interpretations argue for compatibilism, suggesting that free will can exist even in a deterministic universe. This view often redefines free will not as the ability to choose outside the laws of physics, but as the ability to act according to one's own desires and reasons. even if those desires are themselves determined by prior causes. Your choices are free because you are making them, even if those choices were, in a grand cosmic sense, always going to be made.
Furthermore, the weirdness of quantum mechanics sometimes enters this debate. If true randomness exists at the quantum level, if, for example, a radioactive atom decays at an inherently unpredictable moment, then perhaps this genuine randomness could provide a loophole for free will in a deterministic universe. However, it's not clear how random quantum fluctuations translate into meaningful conscious choices that feel like my decision. It's an interesting thought, though. Imagine your decisions being influenced by a tiny, unpredictable quantum dice roll. Ultimately, the question of fate versus free will, viewed through the lens of time, remains one of humanity's deepest philosophical and scientific puzzles. Does the universe know what time it is because its entire temporal history is fixed, or is its future being constantly co-created by the myriad choices of its inhabitants? We might feel as though we are actively steering our lives through the river of time, but perhaps the river itself already knows exactly where it's going. You've made it. Our journey through time's deepest questions has brought us to the doorstep of the ultimate enigma, the universe's timeless riddle. We've probed its strange dance from the Big Bang to the quantum foam, wrestled with its relativistic contortions, questioned its fundamental existence in emergent theories, and even peered into the speculative realm of holograms and multiverses. Yet, despite our advanced physics and ever-improving observations, time remains one of science's most profound and unresolved mysteries. A mainstream scientific fact is that our current understanding of time is incomplete. General relativity describes time as a dimension interwoven with space, bending and stretching with gravity and motion. Quantum mechanics, on the other hand, often seems to do away with time as a fundamental entity, favoring timeless probabilities and correlations.
These two immensely successful pillars of physics simply don't play nicely when it comes to time, especially at extreme scales like the Big Bang or inside a black hole. This incompatibility is the enduring core of the riddle. It's like having two halves of a perfect jigsaw puzzle, but they refuse to click together no matter how hard you try. This leads us to the grand, overarching, open scientific mystery and the subject of continuous, vigorous, scholarly debate. Does the universe truly know what time it is? Or is time merely a construct, an illusion, or an emergent property of something deeper? There's no single, universally accepted answer.
Some physicists maintain that time is fundamental, but our current theories simply haven't captured its full nature. Perhaps there's a more complete theory of quantum gravity waiting to be discovered that will reveal time's true, fundamental role. They might argue that our everyday experience of a flowing, progressive time is not an illusion, but a reflection of a deeper reality, albeit one warped and twisted by gravity and speed. In this view, the universe does have a master clock. We just haven't fully understood how to read it at all scales. Others lean towards the idea that time is emergent. In this perspective, the universe isn't in time, but rather time emerges from the universe's ceaseless changes. The flow we perceive could arise from the increasing entropy, the constant processing of information, or the intricate dance of quantum entanglements. If this is true, then the universe doesn't know what time it is, because there's no inherent independent time for it to know. Instead, time is a consequence of its dynamic internal processes. It's like a bustling city. It doesn't know it's busy, but its busyness is an emergent property of all the activity within it. Think about the implications for your own existence. If time is a fundamental backdrop, then your life unfolds within its fixed progression. If time is emergent, then your perception of sequential moments might be a sophisticated cognitive construction, and your conscious awareness is simply creating a narrative from the continuous change around you. It's a bit like watching a flip book. The individual pages are static, but your brain creates the illusion of movement. Ultimately, the universe's relationship with time is a profound puzzle that pushes the boundaries of human understanding. We measure it, we feel it, we organize our lives around it, yet its true nature remains elusive. It's the ultimate cosmic paradox, a force that defines our reality, yet might not even exist in the way we perceive it. The universe, in its vast, silent expanse, continues its grand temporal dance, and for now, the secret of its clock remains its own. The quiet hum of the night seems to deepen around you, doesn't it? As we drift away from the complexities of cosmic time, let your thoughts gently settle, like dust motes descending in a still room. The universe, with all its mind-bending mysteries, continues its silent, majestic unfolding. Whether time is a river or a tapestry, a cosmic heartbeat, or a symphony of emergent changes, its embrace holds us.
There's a comforting stillness in realizing that some of the greatest questions have no simple answers. It means the cosmos is still brimming with secrets, patiently waiting for inquisitive minds like yours to explore. Imagine the galaxies, vast and ancient, spinning in their slow, grand waltz.
They don't fret about minutes or hours. They simply are, immersed in their own colossal, immeasurable spans. Your own internal clocks, those biological rhythms, are gently slowing now. The rapid fire of thoughts begins to dissipate, replaced by a soft, diffusing awareness. Feel the warmth of your blanket, the steady rhythm of your breath. These are your anchors, your personal guides in the ocean of time. The grand cosmic questions can wait for the dawn. For now, let the wonder wash over you, a soothing wave of understanding that even in the vastness, there's a place for your consciousness, experiencing its unique, precious moments. Rest easy, knowing that whether the universe knows what time it is, you are, for this moment, perfectly aligned with its gentle, quiet unfolding. Let your mind become as vast and peaceful as the starry night sky above, filled with infinite possibilities and the soft whisper of cosmic dreams.